The entire future of our universe, every star, every galaxy, everything that is or ever will be, might depend on the value of a single number. This isn't a story or a metaphor. It is one of the deepest and most startling truths of modern physics. It is a value we have measured, a ghost that haunts our equations of reality, but whose origin we do not understand. This number will decide the ultimate fate of the cosmos. It will determine whether everything ends in a silent, endless freeze, or in a cataclysm so violent it will tear the very fabric of spacetime apart. The story of this number is the story of our cosmic destiny, a tale that begins with the greatest mind of the 20th century, making what he thought was his greatest mistake. It all starts in 1915 with Albert Einstein and his brand new general theory of relativity. His equations were beautiful, a perfect description of how gravity works. They showed that massive objects don't just pull on each other. They warp and curve the very fabric of space and time, and other objects simply follow those curves. But his theory presented a problem. Gravity, as he described it, is always attractive. It always pulls things together. When he applied his equations to the entire universe, they predicted that all the matter within it should be pulling on all the other matter, causing the whole cosmos to collapse in on itself. This didn't make sense. At the time, everyone believed the universe was static and eternal, unchanging. So, to fix his equations, Einstein added something new. It was a mathematical term he called the cosmological constant. In his mind, this constant represented a kind of anti-gravity, an energy that was part of space itself. An invisible, gentle push that would perfectly counteract gravity's relentless pull, holding the universe in a delicate, static balance forever. He didn't have any evidence for this energy. It was an idea born purely to make his theory match the universe he thought he lived in. He had forced his beautiful equations to describe a reality that, it turns out, wasn't real at all. Then, in the 1920s, the astronomer Edwin Hubble changed our view of everything. Using the most powerful telescopes of his day, he observed that the light from distant galaxies was stretched out, a phenomenon called redshift. This meant they were all rushing away from us, and the farther away a galaxy was, the faster it was speeding away. The universe wasn't static, it was expanding. Einstein's original equations, the ones that described a dynamic, moving universe, had been right all along. He had never needed his fudge factor. He later removed the cosmological constant from his work, famously calling it his biggest blunder. For the next 70 years, that's what it was, a historical footnote, a mistake made by a genius. The story seemed to be over, but the universe had another surprise waiting for us. Fast forward to the 1990s, and astronomers were trying to answer the next big question: how much is the universe's expansion slowing down? They knew gravity had to be acting as a brake. The combined pull of all the galaxies and all the matter in between should be gently slowing down that initial outward rush that began with the Big Bang. Two different teams of scientists set out to measure this cosmic deceleration. They were expecting to find out just how hard the universe was pressing on the brakes. Instead, they found it was stepping on the gas. And then, something completely unexpected happened. The observations from the late 1990s, looking at distant, exploding stars called supernovae, gave an answer that no one was prepared for. The expansion of the universe was not slowing down, not at all. In fact, it was doing the exact opposite. The universe is accelerating. Let that sink in for a moment. The space between galaxies is not just stretching. The stretching itself is getting faster and faster over time. Galaxies are flying away from each other at an ever-increasing speed. This discovery was so profound, so utterly world-changing, it earned its discoverers the Nobel Prize. It meant that some strange, repulsive force was at work on the largest scales, a force that was overwhelming gravity itself. Suddenly, astronomers and physicists were faced with a universe that was actively pushing itself apart. They needed something in their equations to account for this mysterious anti-gravity. They needed a source for this cosmic push. And that's when they remembered Einstein's old, discarded idea. There it was, waiting in the archives of physics, the cosmological constant. The blunder was no blunder at all. It was a prophecy. This inherent energy of space, this constant, unyielding outward pressure woven into the fabric of space-time itself, was the perfect candidate to explain the acceleration. This unseen force was given a new name, dark energy, and with that, Einstein's rejected idea was reborn. It returned from scientific exile to become the most important ingredient in our modern understanding of the cosmos. The cosmological constant, once a mathematical fix for a problem that didn't exist, was now the leading explanation for the greatest cosmic mystery of our time. Now, this isn't some small, subtle effect happening at the fringes of the universe. This is the main event. When we add up everything in the cosmos, all the matter, all the energy, this dark energy, this cosmological constant, accounts for about 68% of the total energy density of the universe. Think about that. All the stars, all the galaxies, all the planets, all the gas and dust, everything you've ever seen or even imagined. That makes up less than 5% of what's out there. The vast majority of reality is this smooth, invisible, accelerating energy that we are only just beginning to comprehend. And here, right here, is where we arrive at one of the most profound and humbling problems in all of science. It's sometimes called the fine-tuning problem, but it might be better described as the worst prediction in the history of physics. When our best theories of particle physics try to calculate how much of this vacuum energy there should be, they get an answer. The problem is, the answer they get is catastrophically, astronomically wrong. The predicted value for the energy of empty space is about 10 to the power of 120 times larger than the value we actually observe. That is a 1 followed by 120 zeros. This discrepancy is so enormous it's difficult to even describe. It's a sign that our most fundamental theories of the very small and the very large are missing a crucial piece of the puzzle. It tells us that we do not understand the vacuum of space, the very foundation of reality, nearly as well as we thought. The fate of our universe hinges on a number that, for now, remains an impossible, beautiful mystery. So, how does this one number, the value of dark energy, determine our ultimate fate? Well, it all depends on its precise nature. If dark energy is a true cosmological constant, a fixed, unchanging property of space-time itself, then the universe's acceleration will continue steadily, forever. Over trillions upon trillions of years, this gentle but relentless push will drive everything apart. First, the distant galaxies will recede from view, their light stretched so far it can no longer reach us. Then, even the galaxies in our local group will be pushed away, until our own Milky Way is an isolated island in an endless dark void. This is the fate known as the Big Freeze, or the heat death, a slow, quiet end where the cosmos grows ever colder, darker, and emptier. But what if dark energy is not constant? What if it's something more? Dynamic. There is a theoretical possibility that the density of dark energy could actually increase over time. Imagine that. The energy of the vacuum itself, growing stronger with every passing moment. This idea is called phantom energy. If it's real, then the repulsive force pushing the universe apart wouldn't just be constant, it would grow. And if it grows, the acceleration of the universe wouldn't be steady, it would accelerate. This leads to a runaway effect, a cosmic feedback loop that pushes the universe towards a far more violent and spectacular conclusion. This terrifying scenario is called the Big Rip. It is not a quiet fading into darkness, but a complete and total dismantling of the cosmos, from the largest structures down to the very smallest. The process would be a step-by-step destruction. In the final billions of years before the end, the runaway force of phantom energy would first overcome the gravity holding vast clusters of galaxies together, sending them flying apart. Then, as the force grew even stronger, it would be powerful enough to unbind the stars within individual galaxies. Our own Milky Way would dissolve into a scattered stream of solitary stars. Soon after, the force would overwhelm the gravity-holding solar systems together. Planets would be torn from their orbits and sent careening into the void. In the final moments, the force would become so immense that it would overcome the forces holding matter itself together. Stars and planets would be ripped apart. And in the last fraction of a second, even the electromagnetic force would fail, and atoms themselves would be torn to shreds. The very fabric of space-time would be ripped asunder. So, here we are, standing on this tiny world, looking out into the cosmos, and realizing that our ultimate destiny hangs in the balance, dependent on the true identity of this mysterious dark energy. Will the universe fade into an eternal cold night, or will it be violently torn asunder in a final, cataclysmic event? The answer is hidden in the precise measurement of a single number, a value we are still struggling to pin down. Our cosmic future rests on a razor's edge between a freeze and a rip. And the quest to understand it is one of the greatest challenges in all of science because it tackles the most fundamental question of all. How will the story of everything end? If dark energy is a true cosmological constant, an unchanging property of space itself, then the universe's fate is a long, slow, and lonely one. This destiny is called the Big Freeze, or the heat death. It's not a sudden event, but a gradual fading. The accelerating expansion will continue, pushing galaxies further and further apart until the light from one can never reach another. The universe will become a collection of isolated island galaxies in an ever-expanding dark ocean. Inside these lonely galaxies, the cycle of star birth will slow down and eventually stop as all the available gas is used up. The existing stars will burn through their fuel, one by one, over trillions of years. Red dwarfs, the longest-lived stars, will be the last lights to go out. The universe will fall into a profound darkness, populated only by the remnants of stars, black holes, neutron stars, and white dwarfs. Even these will decay over unimaginable timescales until only a dilute gas of particles remains, growing ever colder and more spread out as space continues to expand. But what if dark energy isn't constant? What if it's something more? Active. There is a theoretical possibility, allowed by our understanding of physics, that is far more violent. This idea imagines a type of dark energy called phantom energy. Unlike a cosmological constant, the energy density of phantom energy would actually increase as the universe expands. Think about that for a moment. As space gets bigger, this strange energy becomes more powerful, pushing space to expand even faster, which in turn makes the phantom energy even more powerful. It's a terrifying feedback loop. This scenario leads to a dramatically different end, a destiny known as the Big Rip. If phantom energy exists, the acceleration of the universe will not be gentle. It will become overwhelming, growing stronger until it can overpower every other force in nature. The end of the universe would not be a slow fade into darkness, but a final, cataclysmic moment where the very fabric of reality is torn apart. The Big Rip would unfold in stages, from the largest scales down to the smallest. With about 200 million years left, the repulsive force of phantom energy would become strong enough to overcome the gravity holding galaxy clusters together. These immense cosmic structures, the largest gravitationally bound systems in the universe, would dissolve. Galaxies would fly apart from their neighbors, each one set adrift in the accelerating void. Then, with only 60 million years to go, the rip would come for the galaxies themselves. The gravity holding the Milky Way together would fail. Our own galaxy would be unbound, its beautiful spiral arms unwinding as its hundreds of billions of stars are flung into the darkness. A few minutes before the end, the force would be strong enough to tear apart solar systems. Planets would be ripped from their orbits, and our own Earth would be cast away from the Sun. In the final, terrible fractions of a second, the expansion would become infinitely fast. The force would overwhelm the electromagnetic force that holds atoms together. Stars, planets, rocks, and every object would be disintegrated into their constituent atoms. And then, even the atoms themselves would be ripped apart as the strong nuclear force, the most powerful force in nature, is finally overcome. Space-time itself would be torn asunder, and all of existence would end. So which will it be? A cold, quiet freeze, or a violent final rip? The answer, incredibly, hinges on the precise value of a single number. Cosmologists use a letter, W, to describe the properties of dark energy. If the W is exactly -1, we get the gentle expansion of the Big Freeze. But if W is even slightly more negative, say -1.01, then we live in a universe with phantom energy, and the Big Rip is our unavoidable fate. Our current measurements show that U is very, very close to -1. But there is still uncertainty. The entire future of our cosmos, every star, every galaxy, rests on a razor's edge. On a decimal point, we are desperately trying to measure with our most powerful telescopes. We are trying to read the final page of the cosmic story before it has been written. This quest is one of the most profound in all of science. We are peering back through time, observing distant supernovae and the faint afterglow of the Big Bang, all to pin down this one crucial number. The answer will tell us not just where we came from, but where all of this, everything we see and everything we are, is ultimately going. It's a story about the immense power of the cosmos and our unique, fleeting moment to try and understand it.